Hi everyone, this is Dr. Smith, and in this lecture, module, we're going to talk about radiation. This is not anything we've talked a lot about before with respect to environmental health or public health or considerations for how this might impact individuals and populations, but it's something you need to know about because it is there, and in certain special cases, certain special populations, there might be some exposure that is a significant health effect for that community that we need to be aware of. So let's talk very briefly about radiation. Okay, the module or the lecture is termed ionizing and non-ionizing radiation, and that essentially is a very important distinction between radiation. We hear a lot, oh, it's radiation. What does that mean? And so you need to be able to discriminate between the different kinds of radiation, ionizing and non-ionizing, and the potential health effects that are associated with each one of those. And so by the end of this, you should be able to define both ionizing and non-ionizing radiation, state some of the most significant differences between those, describe some of the sources and the types of ionizing and non-ionizing radiation, and the health effects associated with both. And then also, just to give you some historical perspective of why we even consider this and how we know what we know about it, we'll talk about some of the major incidents in which a population was exposed to radiation and both the effects from a health perspective as well as the societal effects and the regulatory effects that arose from that. So, radiation. We hear about this term a lot. And the term radiation in general refers to energy traveling through space. So some types are associated with radioactivity, like alpha and beta and gamma and X-ray particles. Radiation can also include neutrons, which are uncharged. We'll go into more detail about what radiation actually is and the distinguishing features between ionizing and non-ionizing radiation and their impacts on public health. When we talk about ionizing radiation, this is the type of radiation or emission that has enough energy to remove tightly bound electrons from atoms, thus creating ions. And you're like, okay, why is this important to me? Well, when you do this to a compound and you create ions, ions become more reactive. They are unstable by nature. And so when you change them by the introduction of radiation energy, then you create molecules that can be more reactive with other molecules. And so the properties of ionizing radiation are actually used to generate electric power, to kill cancer cells. They're used in many manufacturing and therapeutic processes. And so what are some of the sources of these kinds of things? So these are the man-made sources of ionizing radiation: X-rays and other procedures used in medicine. Okay. Certain consumer products like and other things of that nature. Radioactive substances used in industry, so isotopes that are used in industry. Nuclear power generators, radioactive fallout. So this is the sources from production and detonation of nuclear weapons, primarily for testing purposes. What are some natural sources? So we talked about man-made, cosmic rays, things that come in from space. Other forms of radiation that impinge on Earth from space. Solar flares can create, if we think about things like the northern lights, that is a form of radiation impinging on the Earth from the sun and from outer space. Radiation from geologic formations that contain radioactive elements, such as uranium, from which radon gas is formed as a decay product. We could talk about this in more detail a little bit later, but some examples. So there are natural and there are man-made sources. If you think about one kind of funny little man-made source that I didn't mention earlier, things like smoke detectors in your home actually contain a small amount of radioactive material. If you ever look at the label on that, it's not of any danger, it's low enough levels, and it's used in the detection of the smoke particles by ionizing interactive things which set off the alarm. What are some types? There are both particulate energies. These are particles such as protons, neutrons, and alpha and beta particles. We'll talk a little bit more about that, but just know what those are and know the difference between ionizing radiation. So there can be those particles, highly charged particles, or there can be electromagnetic energy in the form of photons, such as gamma rays and X-rays. So it comes in a couple different forms, okay? And this is important. This is actually important in the potential health effects that these can create, because some of these contain more energy than others. Some of these, because of that energy level, tend to be more reactive and create more changes in the biological molecules that they interact with as they encounter them. And so radioactivity in general, you know, we think of people glowing in the dark and things like that, but this is spontaneous emission of radiation from a nucleus of an unstable atom. And so this is the fission or fusion, if you want to look at that from a nuclear power generation or a nuclear weapon standpoint. But as a result of that, the radioactive atom is converted or decays into an atom of a different element that might or might not be radioactive. And this is a whole science in and of itself. And so in the process of spontaneously emitting radiation, an element can actually decay into something else. So we talked about uranium and radon as a byproduct of that. They're different elements altogether. It's a matter of the fact that the uranium has decayed and released energy and created a new element that is the radon. And it's interesting, but again, this is a topic of people spend their entire lives studying. We just want to understand that there are different kinds of radiation and that these can occur spontaneously as well as by human processes that create them, say in the production of nuclear energy for power. I'm going to talk about some concepts around radiation and around dose and exposure that vary significantly from what we've talked about regarding dose and exposure from a chemical toxicology standpoint, which is what we've talked about mostly. So the concept of absorbed dose, this is important because the radiation energy absorbed per unit mass of an organ, and this is how we actually study the effects of radioactivity on human organ systems in the production of cancer or other effects, okay? Now, contrast that with dose equivalent, which is you take the absorbed dose and you weight it to essentially show the biological effectiveness of the particle that produces ionization. So we've got the absorbed dose, which is essentially the external dose of radiation energy absorbed per unit mass of the tissue. And then we have the dose equivalent that shows us what that did biologically, if that makes sense. So you've got a dose, and you think about it from the perspective of chemical toxicity, and if you ingest a certain amount of a drug or a chemical, that doesn't mean all of that gets to where it actually has a biological effect in the system. So if you take a bunch of ibuprofen for a headache, not all of that dose of ibuprofen gets to the source of your headache pain, whether it be neuromuscular or something else, inflammation, inflammatory pain. So we're talking about the same essential concept here, which is the absorbed dose is how much actually hits the target organ radiation-wise. And then the dose equivalent is what portion of that actually makes some difference or reflects some change in that biological tissue from the ionization due to that radiation. Exposure is not too different, but in radiation, we talk about it a little bit differently. And so exposure is used to indicate the amount of ionization in air produced by an X-ray or gamma ray or other particle, and we talk about that as the Röntgen or the unit R. Some other common units of radiation. And so if you think about that from the standpoint of exposure, you're talking about the ambient dose, right? So we're talking about what is actually going on in the environment, in the air, that has a potential to affect the biological dose or the absorbed dose, and then also translates into some percentage as the equivalent dose. In common units of radiation, you may have heard some of these. The Curie, after Marie Curie, early researcher into radiation and radioactivity. It's a unit of measure named after her to describe the amount of radioactivity in a sample of material. She worked a lot with radium, and she would measure how much radiation was given off by a certain amount of that, and that became the unit of measure applied to a material. It doesn't have necessarily dose implications, so it's more of a source exposure. You could equate it to something like the concentration in the water that you drink of arsenic. The amount of the material, i.e. the radium or the other radioactive source, is equated from the measures in Curie. And the RAD, this is the radiation absorbers. This is a former unit. We don't use the RAD as much anymore, but of absorbed dose of ionizing radiation. So absorbed dose is now a more common term. We also talk about the REM, or the Röntgen equivalent in man. So this is a measure of the dose related to a biological effect. So it's kind of the equivalent dose concept, but it's the dose actually deposited in a body tissue averaged over the mass. And so if you think about not external radiation, but if you've been exposed to particles or radiation in an ingested source, and that material deposits in a certain body tissue, then it's the dose from that source and the biological effect that it produces. So, and then the Röntgen is the unit of exposure from the X-rays or gamma. You'll hear that term a lot, but we use a lot of concepts of the REM for non-external exposures, also with respect to the equivalent dose and the absorbed dose. And so factors that expose or that affect the amount of radiation exposure. This is not too dissimilar, although one of the differences in radiation is you don't necessarily have to be, the distance is important, I guess I should say that. The distance from the source is important because some of these particles have a very, they have a high energy but a low transmission. They lose energy very quickly. And so factors to consider are the total amount of time you're exposed, right? Why they pay attention to medical x-rays, how many times a year you get medical x-rays, how long the exposure is needed to actually get an effective or an efficient or a representative image from the x-ray, and why the technicians typically are screened from that because they will be receiving a higher exposure than will the patients in most cases over a period of a year or whatever. And the distance, I mentioned this just previously, but this is important, and we'll get into this a little bit more as we talk about both electromagnetic radiation and particle radiation, and which of the things can have more of a biological effect depending on the location that they're generating the radioactivity from. Is it internal, is it external? That can have a big difference, and it loses power over certain things, certain types of radioactivity lose power over certain distances that render them essentially not an issue. And then the degree of radioactivity, that is, how much energy is it actually putting out per Curie, for example, per amount of that. Is it highly radioactive or is it only moderately radioactive? Some of the acute health effects, remember this is short-term exposure of ionizing radiation, include tissue burns and radiation sickness, that is nausea, weakness, loss of hair, skin burns, as mentioned above. At low levels, the ionizing radiation usually doesn't produce immediately detectable harm. This is more of a chronic thing, okay? Think back to radon, which we'll talk about in a minute. The effects come not from the acute exposure, but from chronic exposure. And at high levels, essentially this can be fatal. If you get a whole body dose of pretty significant ionizing radiation, it can be fatal. A concept here that will carry through and is actually important in not only radiation biology or radiation toxicology, radiation health effects, but in any kind of health effect, and that's stochasticity. And stochastic means that there's an increased probability of the occurrence of an adverse health event. And so you can relate this certainly to risk and probability epidemiology. So we're looking at stochastic effects from the standpoint of, if all the other factors are considered equally, what's the likelihood, the probability of the occurrence based on that exposure of some adverse health effect. We typically use this in association with low levels of exposure to radiation over long periods of time. So stochastic, almost by definition, is chronic exposure and effect. Carcinogenesis and genetic damage, DNA, maybe epigenetic, are some of the things we consider to be likely stochastic effects of radiation exposure. So we talked a little bit about terminology to give you context, and we'll talk now about sources and then go into some details about the types of thing that can produce, why it's a public health concern, why radiation needs to be something to consider. So we did mention that some of the natural sources are cosmic radiations, things coming to the planet from outside, why we wear sunscreen, right? Why it's becoming more important for us to wear sunscreen, why the loss of the ozone layer around the Earth is important, because we're constantly bombarded both with visible and invisible types of radiation in the form either of particles or electromagnetic frequencies. Naturally occurring deposits in the Earth, such as uranium, that can cause increases in radiation levels in certain geographic and geologic areas because of the presence of that material. One being radon, which is the decay product that actually gets into homes and exposes residents and has a pretty significant impact on the incidence of cancer in the population. Some other sources that are man-made: nuclear power under bad conditions, radioactive fallout from the testing of nuclear weapons and other nuclear testing, decommissioned and abandoned nuclear weapons facilities, and storage of nuclear wastes. So we don't talk a lot about this, and you mostly talk about it if you live close to it, but there are places around the world, including in the United States, where we have taken a lot of old nuclear weapons and weapons production material, and because it is fairly dangerous and the half-life for certain of these materials is on the order of thousands to 10,000s of years, we put them in a quote safe storage area, and I can go into some more detail about examples of that with those of you who might be interested, or on a special lecture time. Medical x-rays and radiation diagnostic and therapy procedures. These can produce some exposure to ionizing radiation in the general population that we need to think about. And there are controls around that, both from the clinical side and the patient side. Just to break it down into a nice graphic, here's some sources of radiation exposure. And so it's very interesting that what we see is most of the radiation exposure, and again, depending on a lot of variables like where you live. So for example, if you live in Denver versus living in Loma Linda, Denver is at a mile high and Loma Linda is at about 1,200 feet above sea level. The amount of natural radiation coming in from cosmic sources is significantly greater in Denver, and so you have to make those kinds of background considerations. But in general, this is in the United States, medical procedures in nuclear medicine and consumer products are 50% of our exposure to radiation. The rest is largely radon and thoron, which is another daughter product of radon, in our homes and buildings, and highly dependent on where we live. The geology is a big factor there. We get some from space, we get some from the soil, that's naturally occurring geologic materials, and some from industrial and occupational exposure. So it's basically 50-50, man-made sources versus natural sources. We'll talk about some specific things here. We've mentioned already uranium. very common in the Earth's crust. It's deposited in certain parts of North America, Africa, and Australia in higher amounts. Uraninite and pitchblende are the ores. These are mined and extracted and refined, and that in and of itself poses some danger. And just because it's a naturally occurring element, it's not necessarily a heavy element or a heavy metal, but it's naturally occurring. And so we all have a little bit of this in our systems just because we live on the planet and we're part of the ecosystem. And if you go back to this slide, you look at the internal sources of radiation exposure on the left hand of the graph, it being 5%, that's what we're talking about here. Just because radioactive minerals occur in the environment, they get into the food system, we get exposed to them either through food, water, dust, inhalation. We all have a little bit of this in our systems naturally. When uranium degrades, because it's constantly giving off energy and changing its ionic state depending on how long, how highly charged it is, one of the things it decays into or produces is radon. Now, radon is very interesting. It can come from both the decay of radium, another radioactive element, and uranium. It's inert, it's colorless, and it's very, very toxic. Not acutely toxic, like you would think of nerve gas or something like that, or even carbon monoxide. So if you walk into a room, it's not going to kill you acutely, but it is highly potent as a carcinogen, as one of a fairly short list of compounds that's classified as a known human carcinogen. And this is essentially due to longer-term exposures. It's more prevalent in certain areas of the United States and the world, as evidenced by that other slide. And most real estate transactions, if you're buying a home, again, kind of back to our lead paint thing, if you're buying a home, you will be required to sign a form saying you were informed of, radon dangers, because it's part of the natural geology. So those two naturally occurring things are a huge part of the exposure we face as humans. The other material that comes from outside, we talked about that a little bit. A lot of these things are very high energy. So you've got gamma rays and things coming through the atmosphere. These have the ability to penetrate and cross the human body very easily. If they interact with a substance such as DNA, they can create a mutation and can lead to cancer. Again, why we wear sunscreen and things like that. That's the ultraviolet portion of the cosmic rays, but you can have the gamma rays as well. We also have nuclear facilities, weapons production plant, nuclear power plant. One of the things that is good for us to understand, I try and always put in one or two kind of seminal environmental health events that made us aware of things. So we talked about lead poisoning, and we talked about arsenic, and we talked about pesticides and DDT as kind of seminal events. For nuclear power, nuclear exposure, we talk about 3 Mile Island. And there are some members of the faculty have more in-depth exposure to this or experience with this. This was a situation where in Pennsylvania, it was a large nuclear facility generating electric power, and essentially went to almost a meltdown of the facility and released radioactive material into the environment as a cause of that. It avoided an explosion, which was very good. But as a result of that incident and the safety measures and the control measures, there were no nuclear power plants built in the U.S. for well over a decade. We all, I believe, at least have been exposed to Chernobyl, where there was actually not quite there was no explosion, but there was a significant enough meltdown that huge amounts of radioactive material from the reactor were released into the environment, with consequences that persist today, even in the form of being able to detect that radiation around the globe in certain places. So those are some of the things. When we think about radiation, depending on the era you grew up in, a lot of us think about nuclear explosion. And so the blast from the detonation either of a nuclear power plant that's gone critical, or from a nuclear device used, such as at Hiroshima and Nagasaki. What are the effects there? Well, the blast impact itself can be fatal and destructive in a huge radius around the blast center. Heat, because of the thermal energy released, firestorms created by that, high temperature, intense light, and then the ionizing radiation. So those who are not affected by the first three incidents, or maybe also affected by the first three bullets here, can create different degrees of severity of response because of acute radiation syndrome and the ionizing radiation. And so people near the nuclear explosion would be primarily the thermal burns and the radiation injury, or just the impact of the detonation is potentially fatal. But a major byproduct of that, after the immediate phase, is the fallout, which is ionizing radioactive particles that are released into the environment by the effect of the blast. And so the high levels of radioactivity will dissipate over a few weeks, but these can be taken up the long term into animals and humans. And we saw this actually with the recent tsunami and release from the Japanese nuclear plant on the coast. They were actually able, about 3 to 6 months, I can't remember the exact time frame, 3 to 6 months later, to measure, because you can see a radiation signature in these, measure the radiation that was released from that destruction of that plant in Japan along animals in the California coast and sediments in the California coast. So once again, what happens globally can affect, or what happens in one location can affect us globally. We noticed from the slide and the graphic earlier that medical uses of ionizing radiation constitute about 40 to 50% of radiation exposure that we undergo as human beings, at least in the U.S. Use of X-ray machines, nuclear medicine devices, radiation therapy for cancer chemotherapy kinds of things, or not chemotherapy, but radiation therapy for cancer. So it's a significant amount, but it's also much more controllable than some of the other sources potentially. So those are the things to do with ionizing radiation, and we've got a few examples after we talk about a little bit more about the kinds of particles and frequencies. And so let's talk a little bit about non-ionizing radiation. And this is radiation that has enough energy to move atoms in a molecule around or cause them to vibrate, but not enough to remove electrons. So if you remember back to ionizing radiation, the particular characteristic there was the radiation, or the energy, is enough to remove electrons and make them ionized. In this case, it causes them to vibrate or move around and generate a different kind of radiation than actually ionization. Okay, so not removal of electrons, but just change in frequencies essentially. So we're talking about sound waves, visible light, and microwaves. We're also talking about extremely low frequency radiation, that which surrounds high power lines, AM, FM, TV, radio waves, microwave radiation, infrared radiation, right? So it's heat lamps and things like that. Visible light radiation, these are all non-ionizing types that we're very familiar with, and ultraviolet radiation, UVA, UVB, and UVC. The ELF, or extremely low frequency, does not really, there's a lot of ongoing debate. It doesn't produce a lot of acute or short-term effects, but the higher frequencies, such as high-level radio frequency and microwave, can cause heating of the body, and it does that by agitating the water molecules in biologic material. Some sources of exposure are, again, the electric power poles or transmission lines. wiring in the buildings and some electrical appliances. So you're always exposed to this in modern society. Now, there's been a lot of debate about living under high power electricity transmission lines and the potential health effects that might occur from being exposed to that over the long term. There may or may not be. I think the evidence is somewhat equivocal, and so a topic to expose, but it's something to be aware of. As the EMF or as the electricity flows through that, it produces these electromagnetic fields, and those radiate out actually a fairly significant distance from the transmission lines themselves. So even though they may be 60, 80 feet above a house or something, the field, depending on the voltage that's carried through those lines, can actually extend pretty far around those lines. It's somewhat inconsistent as far as that kind of exposure and cancer or other health effects, but it's definitely something that people continue to study and look at, and we need to be aware of. Think again about if you just want to go off on a little bit of a tangent, you think about where do these power lines run through? Are there environmental justice issues around that? Well, it depends. You have to look at that more closely. Here's another thing that will strike all of us very close to home, is radio frequency and radiation in cell phones. And so cell phones are very low power apparati. They emit in this range here of 900 to 1800 megahertz. And this is a 2009 number. We know this is probably way larger now as far as the number of phones in use worldwide. And so the popularity of these and the constant use of these things, we think about Wi-Fi and using our phones, and it's pretty constant. Maybe even just because of the constant exposure and the widespread use, there might be some small health effects that could be magnified because of the magnitude of the use of these things. And the antenna banks themselves, so the cell phone towers that we see around disguised as palm trees and things, they can also be a source because they're kind of a collection and redistribution point, and so there's a lot more radio frequency radiation. Now, there have been studies done around brain cancer and reproductive effects in men who carry their cell phones in their pockets. I don't know how definitive those are as far as the potential for health effects, but again, something for us to consider. And talk about ultraviolet radiation, and there are a number of sources. Most of us are familiar with this from the use of sun screens, but there are other sources. So welders' arcs are significant sources that can be highly damaging in an occupational setting, even to those who are around not welding. So that's something from an occupational safety standpoint that's looked at very closely. Tanning bed lamps, some of the flood lamps used in photography, although this is not so much, this would have to be the older style of lamps. Halogen desk lamps, certain kinds of lighting, sunbathing, sparks. And so when we talk about excuse me, the UV index, UV radiation is coming from the sun. We divided it into A, B, and C, depending on the wavelength, okay? They're all ultraviolet, but there are 3 wavelengths. And of those 3, the UVB is considered to be the one that is most harmful to humans. And that's what you'll see on the sunscreen bottles now. It used to be just protection level, but now it specifically talks about UV A, B, and C, with B being the most significant source. And we look at the ultraviolet index to help protect exposed persons from excessive amounts of sunlight. And so you can get this on your cell phone, or you can get it from the local weather station. It's kind of what is the severity today, and it typically is on the 1 to 11 scale. It's calculated across the U.S. And as I mentioned earlier, lower elevations have less. There's more atmosphere in the way, and so on a day that is a significant risk day in Denver, it's not going to be as significant a risk in Loma Linda, just because the thickness of the atmosphere will buffer out some of that UV intensity. What do we look for here? If you get high exposure, and this is maybe with the welders or some of the high intensity arc lights, you'll see burns and blinding. That can actually be a significant problem in the occupational arena. Long-term consequences, it's tough on the skin, non-melanoma skin cancer, which you can also get from arsenic exposure, and malignant melanoma, retinal damage, lens opacities if you're not shielding your eyes well enough from all this stuff. So that concludes our brief discussion of ionizing and non-ionizing radiation with respect to public health. I hope you've enjoyed that. Please let me know if you have any questions. Thank you all.